Today, I will be showing you a proof of the parallel axis theorem, which states that the rotational inertia of an object rotating around an axis is equal to the rotational inertia about its center of mass plus mr squared, which is equal to its total mass, plus the distance between its rotating axis and a parallel axis that does go through its center of mass. Now let's just start with any object that is rotating around the z-axis through its center of mass. Remember that the inertia of a point mass rotating around an axis is equal to mr squared. Thus, by summing up all the points in this object, we can say that its inertia is equal to the integral of r squared dm. And since r squared, the distance between the point and the z-axis, is equal to x squared plus y squared, we can rewrite this as the integral of x squared plus y squared dm. Bearing that in mind, we can now consider an object that does not rotate around an axis that goes through its center of mass. In this case, it is still rotating around the z-axis. However, the z-axis does not pass through the center of mass. The equation from our previous example still applies. The total inertia is equal to the integral of x squared plus y squared dm. But we will need to restate x and y for the purposes of this proof. So we can say that the x value of the point we are evaluating, dm, is going to be equal to xcm plus x prime, where xcm is the x position of the center of mass, and x prime is the x distance between dm and the center of mass. And y is equal to ycm plus y prime, where ycm is the y position of the center of mass, and y prime is equal to the y distance between the center of mass and dm. So, substituting in these values for x and y yields our next equation. This, in turn, multiplying out each squared term, will give us this equation. Then, splitting the integral apart into many different integrals, we get this equation. You may want to pause the video now to check for yourself that these equations are indeed mathematically identical. So now, all we have to do is show that this equation is equal to I about the center of mass plus mr squared. And what we can do is we can show that the first piece of this equation, highlighted in the red, is equal to the inertia about the center of mass. Here, x prime and y prime are the differences in x and y values between dm and the center of mass. Looking back at our original equation from our first object, it should strike you that this is mathematically equivalent to the object's rotational inertia about its center of mass. Now let us show that these two parts of the equations, highlighted in blue, are also mathematically equivalent. In the top equation, x value of the center of mass and the y value of the center of mass are constants. And, due to the Pythagorean theorem, x squared plus y squared is equal to the distance squared between the z-axis and the center of mass. This is the r squared in our final equation. And because there is an integral, the dm will simply become m, the total mass of the object. And so we can see that this piece of the equation is mathematically equivalent to mr squared. You may be wondering about this final piece, highlighted in the green. Well, since we've accounted for all parts of the equation already, all we need to do is show that the part in the green is always equal to 0. Here I will be focusing on these two parts of the equation, now highlighted in green. If we can show that both of these are equivalent to 0, then we can show that the whole expression is equal to 0. Okay, so let's take a closer look at both of these expressions for a minute. Remember that x prime is the distance between dm and the center of mass in the x direction, where y prime is the distance between dm and the center of mass in the y direction. And because the center of mass is indeed the center of mass, this means that there is an equivalent amount of mass above the center of mass in the y direction and below the center of mass in the y direction. Likewise, there is an equal amount of mass to the right of the center of mass in the x direction and to the left of the center of mass in the x direction. And so from this, it should be pretty clear that if you integrate every single point of the object using its x and y distances from the center of mass, the masses on the right side and the left side of the center of mass will cancel each other out, resulting in 0, and the masses above and below the center of mass will cancel each other out, resulting in 0. So there you have it, the proof to the parallel axis theorem, again, which states the rotational inertia of an object is equal to its rotational inertia about its center of mass plus mr squared. Thank you.